Here's what that equation really says. Okay, I'm going to write it in its absolute long form one time, and I'm probably going to stop like halfway through. Okay, I would take kinetic initial plus gravitational initial plus elastic initial plus chemical initial plus nuclear initial plus light initial dot dot dot. And then I would have to, all of those would equal kinetic final plus gravitational final. Basically, the long form of this equation, which heads up, you're looking at that like that's a lot we're not going to use, okay, is ridiculous for a couple of reasons. But the main one is you have to write 9 types of energy on one side, 9 types on the other, and then you'd have to find equations for every single. That just feels like a lot of work and a lot of extra work. So we're going to do 2 things to make it simple. First thing is just a basic logic thing. It's this. You may know this, you may not. If you don't, let's talk about it briefly. Does this mass have nuclear energy? Try again.
Yeah.
The fact that I use the word "it has mass" means it has nuclear energy. Okay? Meaning, you'll find this out eventually when we start talking about it later this year, all mass can be converted to energy. The amount of energy in this is about twice the amount of energy as the bomb that destroyed Hiroshima. So if we converted all of the energy inside of this to energy, it would be very bad for all of us. Luckily, it's ridiculously stable, and we do not plan on that happening. So, is there a large amount of nuclear energy here?
No.
Yes. So initially, there's a very large amount of nuclear energy. But at the end of this, will it still be that same number? Yes. And mathematically, if I have 3 times 10 to the 8th joules on one side and 3 times 10 to the 8th joules on the other side, what will it do? Cancel. So do we need to concern ourselves with any types of energy that are not changing? No. Which really goes back to work because it's all about changing energy, but we'll burn that bridge a little bit later. Meaning, you don't got to write all 9, you just have to write the types that are changing. But we're going to make it even simpler than that to start off with. We're going to do a gross simplification. But before we get there, let's have a conversation real quick in terms of conservation of energy. Okay? Imagine you have a roller coaster that is designed utterly and terribly poorly. We have a roller coaster right here on this first hill, and it's designed poorly because the second hill is taller than the first, and it's dropped from a rest over here. So it does not have kinetic energy. So, discuss in your group why that is a terrible design of a hill using conservation of energy at the heart of what you're going to say. Discuss real quickly. We'll be right back. It won't be long, 30 seconds, 40 seconds.
So when you're trying to find the using all conservation you go down, but it's not going to have any more potential than the other here, so you can't create the energy, so then it's not going to.
All right. Let's start off with conservation of energy. Hey, we start with gravitational energy. If I made up a number, it's way too simple of a number, but let's say it's 100 joules. That's way too small. Don't worry about the specific number. It's just a number to be a number, okay? That means it only has 100 joules of energy. Why is this a terrible designed hill?
Because the potential energy of where the height that it's at is only going to have that height, like have that potential energy, like because when you go down, you can't create any more energy, so it can't go higher than where it's at.
I'm going to say that a little bit differently, but that was pretty correct. Okay. The idea is conservation of energy means if I start with 100 joules, I can't go past 100 joules, right? Meaning the best you could possibly do is get that exact same height on the other side, right? Now, that being said, let's change it to another poorly designed hill and discuss why even this one, well, is a little bit better than the first. This is a roller coaster in which the hill, the second hill, is exactly the same size as the first hill, okay? In reality, not based in like assumptions, why is that actually never going to happen? Or if it helps you, this is the conversation from yesterday where I said, hey, this starts off as 10 joules. You ever going to expect it to actually get back to 10 joules? No. Okay, discuss quickly in your group, why is this one poorly designed?
And then probably also, even if it didn't lose any energy for
Okay, all right, so why is it a bad idea?
It has other forces.
I want you to add a little bit to that. It's 100% right.
There are other forces acting upon it.
So combine those together. The other force that we are.
It's losing energy when other forces are acting upon it.
A little bit more specific. Think conversation yesterday. You're doing great. You're doing amazing. I appreciate that. Just trying to pull out. Let's go. Somebody else here. Help us out here. Yeah, he's non-conservative forces. So what does that mean?
Sound and.
Oh, hold on. You're kind of skipping around there. Non-conservative forces is friction. That's what's doing the work. That's what's doing the problematic thing. So what I would hope that you say is, because of non-conservative forces, what's going to happen to mechanical energy? It's going to go to something else. So conservation of energy is a law. It's always, always, always a thing. Meaning, what's going to happen here is this thing's probably going to get to like 80 joules of potential energy. So does that mean it lost that energy? No, it just means the 20 joules is probably in what two other forms on a roller coaster?
Being transferred.
Sound and thermal, correct. Yes, the fact that you hear a roller coaster at all means it's going slower, by the way. So yeah, that being said, that second rule with work non-conservative brings me back to the next simplification we're going to make to this. Well, actually, no, this guy right here. Okay, we said this yesterday. You go away. I don't need you yet. What are you doing here? Thank you. Okay. The second assumption we're going to make right now, which is a big assumption, and I promise to fix it later, okay, is we are going to assume only conservative forces are doing work. Is that reasonable? No. No. Which major force are we probably going to be ignoring the most? Friction. We're going to be ignoring a lot of friction in this particular case. I promise to bring that back later, make it a lot more realistic, but essentially we are going to assume on this picture for right now that in this scenario, if they were the same size hill, that this would just come right back to that same size of hill. Again, not terribly realistic, but it does give us a really good spot to start. So if you will, you can kind of think of this like kinematics. It's a model. It's not perfect, but it's pretty darn close. Now, if that's the case, if only conservative forces do work, what's going to happen with our types of energy? It's going to stay over here. So with that giant assumption, and I add that it's an assumption because it's not based fully in reality, we are not going to do conservation of energy. We are going to do somewhat close to that. Come on, stop. So help me. Quit it. Quit it. Quit it. We get it. We got it. Okay. We're going to do conservation of mechanical energy. Once again, I reiterate, is conservation of energy a law? Is it always going to happen, conservation of energy? Yes. Is conservation of mechanical energy an actual thing? No. In order to pull off conservation of mechanical energy, we have to be making an assumption that only conservative forces are doing work. Now listen to that carefully. There can be non-conservative forces in the problem. They just can't be doing work. Fair? Okay. Now, I'm going to kind of reform briefly here what mechanical energy is. I said the other day, it's not a difference, but it's kind of a different way of looking at it. I told you the other day that mechanical energy is a category where all the types of energy are easy to measure. Here's another way of saying it that I think your textbook actually used and probably most of you wrote down in the definition. Mechanical energy is the sum of all of these type of energies. In other words, the full form of this equation right down here, if you have to write it all out, order doesn't matter, is going to say this. All the mechanical energies initial equal all the mechanical energies at the end. And that's what we're going to use today. I'm going to try to show you in a situation how you know you can use it, how you can get a feel for whether or not you can use it, and actually the process of using it is super, super simple. But ultimately what it says is this. If I add all these numbers up, and I get 400 joules. What's going to happen if I add all these numbers up? 400 joules. And if you just trust that, that's fair, that's reasonable. It's a weird thing. That's why we have a lab tomorrow. So that hopefully you can see that, yeah, actually it's pretty darn accurate. But let's move on. We're going to begin today. I'm actually going to close this because I don't want those. Don't save. Bring you back up. Slideshow. Current slide. There we go. All right. We're going to begin with the problem of a roller coaster. Right? And we're going to use conservation of mechanical energy. So what force am I probably going to ask you to ignore? Friction. Okay. Now, if I don't straight up say that on a problem in mechanical energy, you know that if I'm asking you to use mechanical energy, I am asking you to do that. On the test, I would definitely say, hey, you're going to ignore friction so that you can try to get a sense of it. So we have a 200 kilogram roller coaster. It starts at 42 meters and is going to drop to 0 meters, or position B. Okay, and then you'll notice a couple other spots, C and D. We're going to try to calculate the speed and kinetic energy at spot B. So let's do that over here. Here we are. All right. So we know the mass is 200 kilograms. We know the height is. Let's talk real quickly about this, though. Actually, no. Let's go into this. Let's actually go into this. Let's start with a force diagram. Okay. Why would I start with the force diagram? Well, let's pretend you don't know what we're going to be practicing in just a second. This is how you figure out what you can use. Am I supposed to use work kinetic energy theorem, or can I use conservation of mechanical energy? I'm just going to pick a spot and do a force diagram. All right. Force of gravity is down. Force normal is perpendicular. I'm ignoring force friction. Two forces up here. What are the conservative forces? Gravity and spring or elastic, whichever one you want to call it. Okay. So that means normal up here is in fact non-conservative. But is normal going to be doing work? No. Since it's not going to be doing work, since the only thing going to be doing work is gravity, we can use conservation of mechanical energy. Yes.
Wait, so why is elastic there?
What do you mean? There is no elastic up here.
You said
I
that
asked what the two conservative forces were. They are always gravity and elastic.
Oh.
Sorry.
Okay.
They're not up here. Like gravity's up here, elastic is not. I'm not trying to say that. I just asked what the conservative forces were. Okay, so here's how you start. You write this out to show me that you're using conservation of mechanical energy. The next thing that you do is, listen, if you just want to turn your brain off, write all three types on both sides. If you want to be a little bit more efficient, remember we don't need to worry about types of energy that aren't changing. So, to that point, is there elastic force up here? No. So do we have to write types of energies on both sides then? No, we can just worry about the ones that are changing. So I asked the question, is kinetic energy going to be changing throughout this? Is the speed going to be changing throughout this? Yes, so I write it on both sides. Is gravitational energy going to be changing throughout this? Yes, so I write it on both sides. And actually, I'm going to change a thing real quick. I keep using initial and final. And it's because it's what you're used to. But actually, in this case, it is not helpful because we're dealing with a bunch of different spots. So I'm going to change what I'm not going to use initial and final. If you want to, that's fine. You don't have to erase if you don't want. I'm going to change this to A and B. So this is the kinetic energy at A. This is the gravitational at A. This is the kinetic energy at B. And this is the gravitational at B. We're going to assume that it starts from rest, even though, again, that's not fully accurate because it would have to move, blah, blah, blah. So what I would do next is one of two things. For me, I'm going to cancel what cancels, okay, if you have a good gut feeling of this. If you don't, plug in your equations, and the equations will cancel it for you. So let's talk about what cancels up here. What cancels up here? Okay, A. Yes, the kinetic energy at A. You're fine. Potential energy at B. Let's talk about that briefly, because the way I set this up, 100% you're right, but I do want to point out with gravity, we talked about this yesterday. Let's talk about that equation for a second. Does that have gravitational energy?
Okay.
So, point being, both of you are correct. You get to decide where zero gravitational energy is. If you said that this was zero, and that means I would calculate the height from here, right? And then I would kind of lift it up here. Let's say that's 2 joules, okay? And if I dropped it from here all the way to the ground, it would spend 2 joules of energy. But what if I drop it on this table? And actually, if I drop it, I don't want to break it, but assuming that I did, does it end at 0? No, if I knew that was going to happen, wouldn't it make sense to make this my 0?
Yeah.
If I make this my 0 instead, that's fine, but what that does is it changes the height, right? The height is now from here to there, so it would be like 1 meter, meaning this would not have 2 joules compared to the ground, it would have 1 joule compared to this. Then, pay attention to this, if I were to drop it, assuming that's 0, what would it head into down there?
Negative.
That does happen with potential energy, because energies are just positions in energy. Think about it. If I went from 1, this is 0, that would make that negative 1. And if I drop from 2 to 0, or I drop from 1 to negative 1, isn't that the exact same amount of change in energy? Isn't that the same situation? So, that is all to say, when you do a problem like this, you decide where the 0 is. You're going to get problems today where some of you might decide one, some of you might decide the other, but I agree, let's go ahead and make this a 0. Also wanted to point out that in this drawing, I tried to demonstrate that this is actually the ground. So you're not actually making the 0 the ground, you're making the 0 the bottom of the roller coaster because it makes the math simpler, which is just fine. Okay? Point being, you don't have to make the 0 the ground if the math is easy. Joe.
Why is Ka 0?
Why is Ka 0? Because I said it wasn't moving at the beginning.
So is Ka initial?
Well, Ka is...
To be kidding.
Yes and no. Ka is the kinetic energy at A. The reason why I highlight this, okay? The reason why I highlight this is because there is no initial and final here. Energy doesn't give a crap what's happening between 2 spots. Okay? And if there's a conservation of mechanical energy, like I'm going to make up a dumb number, like, I don't know, 82,300 joules. Okay? 82,300 joules at A means guess how much energy is at B? And more importantly, guess how much mechanical energy is at C? And D is the same thing. So, that is to say, initial and final kind of implies that you have to start here and you have to go there. And then when we start looking at C, you have to start here and you have to, no. Can you compare B and C? Sure, they're equal. Can you also compare A and C? Sure, they're equal, right? So initial and final is a little bit of a misnomer here. As a matter of fact, if this was reversed like Mr. Freeze, it would be completely the same. If instead of being dropped from the hill and going this way, as long as I gave this a kinetic energy, the exact right amount of kinetic energy at the beginning, the kinetic energy plus gravitational would go back through this the exact same way as it went, so the direction doesn't matter either. All right, let's head over here. Sorry, question.
Okay, so when you said that there was negative energy, so like I know you said it was position, but I'm still a little confused on that because you said that it
Gravitational.
can't be destroyed.
Gravitational, it was not destroyed. Negative doesn't mean it's being destroyed, it's just a position. It's just saying like, hey, I'm dropping from 1 to negative 1. How much has it changed? 2. So how much kinetic energy am I going to get out? 2. If I'm dropping from 2 to 0, that's the same thing. We'll see a problem here a little bit later where I think that'll help a little bit more. But let's get back up here. Now, the problem asked you to find 2 things. One, it asked you to find speed, but it also asked you to find kinetic energy, and I'm going to show you the easy way of doing both. Okay. For starters, right now when we come over here, usually what we do is we start filling out all the equations. Somebody kind of just plugging and chugging this, not going carefully, you're just going to plug in both equations and move on. But if I plug in the equation right here, and I don't plug the equation in right there, do I already have the energy for kinetic? Yeah, because all that says is, hey, I calculated how much energy there was in gravitational, and that's the only one. So guess how much total energy I have to have? That amount. So guess how much kinetic is over here? That amount. On the other hand, I'll answer this and just be right with you. On the other hand, if you want to find the speed, Well, then, instead of this, you would write its individual equation. Let me finish this first and I'll be right with you. Doing this way, what mathematical nice thing happens? Why does mass cancel?
Because you're divided by that mass.
Because it's in every term. Remember that, because it's in every term, because that will not always be the case. Here, it's in every term, so it does. It cancels here. Does it cancel up there? No, absolutely not. It doesn't. So, do your algebra here. Multiply both sides by 2. You get 2GHA. Then square root both sides. You get VB. Go ahead and calculate what is the total kinetic energy and the total speed at spot B. You had a question.
Me?
You did, I thought. Oh, sorry, Chloe. I'm sorry. My apologies.
Potential gravity would be canceled
Because there was no height to B.
zero.
Height was 0, because we decided that was going to be our 0. Keeping in mind, by the way, don't forget, G is not negative naturally. G is just a number. We make it negative.
What is the mass again?
200.
200.
So what'd you get for kinetic energy at B? And also A. Well, gravitational with it.
It's the height of
42. You gotta know that's the answer to like everything, right? Is kinetic energy of B? 82,300. 200 times 9.8 times 42.
And then you square it?
Whoa.
Oh,
I asked for
square.
kinetic energy, guys.
Yeah, that's what I was gonna say. I was like,
I was
like, that's a
Finding
really
speed,
low number,
right.
guys.
You're
I was
finding
doing
speed.
cool.
82,300 is the kinetic energy. Be careful there. I noticed on your quiz a bunch of you guys screwed this up, which is fine, but make sure that you don't, because you did a bunch of extra work that you didn't. On number 2, I asked many of you to find kinetic energy final. Most of you went to go find the speed, which I didn't ask for. Which is, again, you can get that, you can use that, okay, but I didn't ask for that. Speed and kinetic energy, not the same thing. One is how fast you're going, the other is how much energy you have because of how fast you're going. That being said, if Spainhour is running at you and a full grown linebacker is running at you, are they running at you with the same amount of kinetic energy? They have the same speed, but not the same kinetic energy, so it's definitely not the same thing. All right, what is that? 2G20 times 42, you get like 28-ish? What is it at? 28.6 meters per second, which is stupid fast. It's like 65 miles an hour. It's insanely quick. Now, here's what I want you to do, okay? I want you to take those ideas and go find kinetic energy and speed at C. Now, if you look at the problem, I also asked you for D, so I'm just going to give you this heads up. If you do this right, the way I've presented to you, it takes very little effort to move between C and D. If you do your equation correctly on C, the work that you're going to need to do for D is super, super, super simple. So go ahead and find, just like we just did, same type of idea, except now you are finding the everything at spot C. Now, again, I reiterate something I said a second ago to help you out. Do you have to compare B to C just because they're right next to each other? No. Me personally, I'm going to compare A to C because I think MGH is a lot easier of equation than 1/2 mv squared. That's just the only reason I'm deciding to do that. I'm comparing those two. Okay? I'm going to quietly do my work up here. Please try to do as much of it as you can on your own. But if you are stuck at any point in time, you're going to see me doing the exact same thing that you're doing up there, so you can kind of watch along on what it is I'm doing. Again, you're taking the exact same numbers and trying to find the speed at C and the kinetic energy at C. I'm actually going to go find kinetic energy at C first. 32 meters is what the height C is at. I'm doing also heads up some extra work up here that I wouldn't have asked you to do to explain something in just a second.
Can you go back to the picture?
What do you need?
The height of C.
32. Isaiah, how are we doing?
What's your shirt? What's your? Yeah. What's happening?
It says, ooh, ah. That's it, I'm not going.
Oh, it's the Grinch.
That's the first comment you guys. If you guys have noticed, I've worn a sweater, like a Christmas sweater,
Dude,
every day since
I've
Thanksgiving.
understood what they were before that.
Yeah.
That was a robot. And I was like,
Do you have your Christmas tree up yet?
Oh yeah, first day after Thanksgiving. Christmas lights are proving a little bit more elusive because I gotta go to Lou's bedroom to go put them up. The problem with that being usually the time that I have to do it when he's napping, when he's in his bedroom. So, not got those logistics. I should have done it last night because Graham had it last night. I just napped. Did watch a lot of YouTube. Got into a new auto battler. You guys heard of Backpack Battles?
no.
It's a demo right now. It's completely free. You should check it out. That's right. No, you're doing physics right now. Don't get involved in video games when you're doing physics. Or high level science. What's that? I love it so much. It's a fantasy setting, but what you do is you buy items, essentially like a sword or whatever, and they go off in a particular time. But the main thing is you have to like reorganize the backpack so that this star is hitting this thing, and it's you gotta just it vibes well with my brain.
Oh.
I got a build last night where I used a pan and surrounded it with food, and it was like my mana was building up, so the food would go off all the time. And I got a bunch of empowered carrots, and so I was hitting people super hard and critting nonstop. So I got like I won like 15 out of 18 times.
Crazy.
All right, let's talk over here. So here's where you have to start. Okay, if you are struggling, listen to what I said to her. You have to start and go piece by piece. So conservation of mechanical energy between A and C, or you could have done between B and C. It doesn't matter because it's equal. I chose A and C because I felt it to be easier. So I break it down into the types of energies that are changing. Just like last time, it's just gravity and kinetic that are changing. Kinetic A cancels because once again, at spot A, it's not moving. Yes? Now, unlike last time, neither of these cancel. Why do neither of those cancel? Well, let's see. Is there a height at C? Yes, absolutely there is. Is it probably going to be moving with the velocity at C?
Yeah.
Yes, absolutely. So that doesn't cancel anymore. So I went about this in two different directions that you did not necessarily have. I went three directions. You have to do all of them. But the first thing I did is just to find KC, I just subtracted this over, and this is me going this direction. So here's what this mathematically says. Hey, if I take all the energy I start with, that's got to equal all the energy over here. So if I subtract how much energy is in gravitation here, the leftover better be kinetic. Simple numbers, let's say I started with 20, okay? If I started with 20, that means that this spot over here, it better also be 20. So if gravitation has like 12, that means kinetic has to have 8. Cool. Now, to do this, a couple things you don't have to do, but I like for simplification purposes. M and G are the same in both, so you can't cancel them because it's over here, but you can factor them out. So I take 200 times G times 42 minus 10 and get 19,600 joules. Now, that being said, if I do it that way, I could do one of two things. Either one, with kinetic energy, I could set it equal to this equation and go find the speed that way. Okay? Then, I did it another way, which is probably more likely to the rest of you, and that is, instead of going that direction, what I did is I filled out the equation for everything. Once I fill out the equation for everything, masses do in fact cancel, so everything down here is just basic algebra. Multiply both sides by 2. Biggest mistake students make when multiplying by 2 is forgetting that you're not moving it from one side to the other. You're multiplying everything by 2. So you either put a 2 in front of that one and a 2 in front of this one right here, or you put a 2 in parentheses so everything multiplies by. I also factored out the G again because it's the same in both, and you get 14 meters per second. And of course, then you can come over here if you wanted to. If you had done this way to get kinetic energy, you could just plug it into this equation and you would still end up with 19,600 joules. So that was all to say again, I did this 2 directions. If I were one of you guys, I would probably either go, everybody goes here and either go this way to that spot, or I would go this way to that spot. I don't care. Questions, concerns here? Yes, AP.
So if you go to the right, are you just setting 19,600 equal to the?
Yep. It just goes.
V squared?
Yep. Just set it right here. Go find V. It'll still end up with 14.
You don't have to redo the.
No, you do not have to go this way and that way at all. Okay. You have every option up here. A lot of energy is going to be like, well, you could do this, or you could do that. As long as you do them right, both should end up with the exact same answer. Okay. Couple more problems to go through. This next one's going to go pretty darn quick because I really want to get to the last one. All right, so here we have a spring compressed 20 centimeters. A spring constant is 200 newtons per meter, and it's pushing a box across a frictionless floor. So once again, let's look at this and go, okay, should I use conservation of mechanical energy? Here's once again how you decide. Start with the force diagram. Why do you do this? Force of gravity down, force normal up, force spring or elastic, I don't care. Okay, now the only non-conservative force in there is normal. Is normal doing any work? No. As a matter of fact, gravity's in there, but is gravity going to be doing any work? No. The only one doing work is spring, but lucky for us, spring is conservative, so yes, we can do conservation of mechanical energy. So here I go, grabbing this picture real fast. There. Come on. Don't, I got too much stuff to do. Don't slow on me now. Okay. Reminding you of numbers that were there a second ago. What it says is that it is currently compressed. It is currently compressed 20 centimeters. It said the spring constant is 200 newtons per meter. It said the mass is a half a kilogram, and it wants to know the speed that it's leaving. The next thing that you kind of need to do in these examples is figure out where's the initial and where's the final. The initial, or A and B or whatever, okay? One of them's got to be where you know most of the numbers. So I'm going to start here before it's taken off. You can see, by the way, that this is compressed, right? Like this is kind of like this is essentially kind of a simplified version of a Nerf gun. The Nerf gun is cocked, ready to go, and you're about to fire it. Cool? Cool. All right. So there's my initial right here. Here's my final. Let's go conservation of mechanical energy. And once again, start the same way we always do. What type of energies are going to change here? Agreed. Why not? Agreed with that? Why not gravitation? What's that? That is one way to say it. That is correct. I would actually say there's an easier way for most people to see it, and that is this. Height's not changing. Does it have gravitational energy? Don't care. Doesn't matter. If this thing's on a table, let's say it's on the floor versus on the table, wouldn't matter if it's on a table, and I want to say it has gravitational energy, because if gravitational energy isn't changing, What are those numbers doing to each other? Canceling each other out. It doesn't matter if it's not changing. So here we go. Here's my setup. Once I get this set up with individual ones, now I can go, what is 0 here? Why is kinetic initial 0? I agree. Because right here it's not moving. Okay. Should it have kinetic final? Yes, because it's going to be moving. All right. What about elastic? And there are zeros here. Yes. Why is final 0? Another way to say that is it's not, two ways to say it. One, the spring is probably not going to push the object anymore, right? The object has left. Even if the spring's going back and forth over there, it's not going to do anything, okay? Or it can be, it's like a rubber band shooting through the air. Remember the band goes like that. Here we go. Okay. Is there elastic currently in the rubber band? When is there no longer elastic in the rubber band? The moment it leaves my hands. Why? Because it's no, what's that? It's back to its original form. It's no longer stretched anymore. The moment it's no longer stretched, it's at 0. All right, let's fill in our numbers. Let's fill in our equations. What's the equation for elastic energy initial? And that, make sure that you put that initial on delta x. Okay, what about kinetic energy final? Okay, a couple things to point out here that I think you're probably good on. First one is this: does mass cancel? Enough students that I have seen attempt to cancel mass in this problem because Sveinarr said it cancels in one case, so it must always. Why does it mass cancel here? It's not in every term. It's just not in every term. If you want to, you can divide mass across there, but of course it's not going to cancel on one side, it is on the other. What technically does cancel? 1/2. Yeah, either divide by 1/2 or multiply both sides by 2. In either case, boom, there you go. So to find speed, go ahead and divide mass on both sides and square root. Now we just have plug and chug. And make sure everything has the right units. I'm going to put this in here. Does K have the right units? Yes. What units does delta x need to be in? Meters. Your biggest clue to that is right here. The fact that this is newtons per meter means this guy right here better be meters, 0.2 meters. Is mass in the right units? Yes, it's in kilograms. The main reason you know that is we have newtons in the problem, and kilograms are buried inside of a newton. .2 squared is 0.04. Multiply that across 20, you're going to get 2 times 4, that's going to be 8. Divided by 1/2 is going to be 16. Square root is going to get you 4 meters per second, if I'm not mistaken. I said that like that was impressive. I did this problem last time. Really wanted to get to this last problem, mostly because I just think it's a cool situation. And it's a good practice, and we're probably not going to fully finish this problem today. We'll probably finish the first part. Whatever we don't finish today, I'm going to ask that you do for tomorrow. I don't care if you do it perfectly. I don't care if it's correct. I just care that I see the work for you to try. So, a 55-kilogram sister bungee jumps off of a 60-meter cliff over shark-infested waters. Now, that is not a nun sister. That is actually, I have 2 sisters, 2 younger sisters, and both of them went to Uganda for the semester in college, and both of them bungee jumped over the Nile. So this is actually a 100% realistic situation, except for the shark-infested waters. I might have added that particular argument. But, you know, you got to give it a little bit of flavor. So, the question on the table is, if she's 55 kilograms and the rest length of the bungee is 20 meters, obviously not drawn to scale over here, the cliff is 60 meters, and she's going to stop 4 meters above the water, what is the spring constant in the bungee cord? Now, to set this problem up, first thing we do is we do kind of a quick force diagram. As she falls, to begin with, what's the only force on her? Gravity. Then, after about 20 meters, what's going to happen? Force elastic. But both of those are conservative. So can we use conservation of mechanical energy? Yeah. So we decide where our finals and where our initials are. Where does it make sense to put the initial? And by the way, I want to specify, again, what we talked about with Joe. When I say initial, it doesn't mean it has to come first either, right? It's just one spot versus the other spot. Where probably makes sense to be the final? Yep, right there. Okay, let's do this thing. Now, again, after you've done this, it's what type of energies are changing. So, give me one type of energy that's changing. Gravitational makes sense. So I'm going to put it on both sides. Next. Elastic, yes. Okay, this next one is a little bit confusing. I think it has two answers, so give a heads up if you look at this situation. Is kinetic energy changing? Okay, if you pay attention, the answer eventually is no, and I'll show you that. But what I would suggest is if it's changing throughout the situation, which you're 100% right, it is changing throughout the situation, I would write it up here, okay? Meaning, obviously, she's going to speed up. Obviously, she's going to slow down throughout this situation, blah, blah, blah. But if it's changing, I would suggest you write it. Then, when we proceed to this next part where we cancel, you're going to notice we're going to start with kinetic energies. What's the kinetic energy initial? Zero. Why? Why is it zero? She's not moving at the very beginning. What's kinetic energy final? So in that way, it's not changing, but it was changing throughout. You want to put it up here for your own edification, as well as sometimes there's problems where there's like a second part or a third part, like in this particular case. So you kind of want to keep in mind these particular ideas. But yeah, in this case, it does cancel out to zero. Let's go, what else cancels here? We'll talk about that in a second. Elastic, which one? Elastic initial. How come?
Because it hasn't jumped in.
Not quite.
The delta X is not like.
I want to say that less mechanically. You're right, but let's say it a little bit less mechanically. Hasn't been stretched. Correct. Yes. Yes and yes. Okay. All right. Very good. Now, someone just said gravitational final. Sorta. Who does that depend upon? Us. There's two logical places to put the zero here. Okay. Both kind of make sense, and then you have to change something if you do it one way. The first logical place is to put it at the water. If you put it at the water, does gravitational final cancel? No. No, it doesn't. Why? Because is it at the zero at the end? No. So does it have gravitational energy right now? Yeah. Yeah, it does. Okay. The nice thing about putting it at the zero is you'll notice all of your heights are already nicely measured from the water, which makes sense. Okay. But what is the other logical place to put the zero? Which is fine. Which one do you prefer? You want the water? Everybody is good with that? Okay, I'm fine with both. Last hour chose this one. I just want to say, if you do choose this one, the thing you have to change is that height up there is no longer 60. What is that height up there if you make that zero? You have to change the heights to match this spot, not the others. Okay, and you'll notice, in our case, if we make the zero the water, which is what you guys just decided, so it's what we're going to do. If you make the zero the water, okay, then you're going from 60 to 4. If you had moved the zero up, then you're going from 56 to 0. Is it the same difference either way? Yes. But since you put that zero there, gravitational final no longer cancels. So here I go again, all on my own, down the only road I've ever known. Like a twister. I was born to roam alone. You know, I've done made up my mind. All right. My apologies. So just filling out all the individual equations and honestly just doing algebra past this particular point. Okay? First thing I'm going to do, since I'm trying to get the k by itself, is make all terms that are not have the variable in them move to the other side. So what am I going to do with this guy here? Subtract it on both sides. Yay, whiteboard. Okay. Then, and again, I cannot stress this enough, when you multiply by 2, remember you're doing that for everything. So here's what I'm going to do personally. I'm going to put a parenthesis around this. I'm going to multiply both sides by 2. Then I'm going to divide by k. The way I personally divide by k is, oops, nope, that was dumb. That was very dumb. We're trying to get k by itself. That would be dumb. Divide by delta x squared. And there we go. Let's plug in. It's weird to not be square rooting something, but there it is. I'm going to come back to this in a second, so just a heads up. You could do it ahead of time. I just want to talk about it at the end. What's mass? Oh, let's factor that out. Good night. Why am I doing all this extra work?
Will the answer be the same if you put the 0 up or no?
Yes, exactly the same, because I'll show you right now why. That's 60 and that's 4. When I factor, actually, let me do it real quick. I'm going to write this differently.
Put it the other way.
I just factored out M and G, so this is, will it be the same if I go 60 minus 4 and 56 minus 0? Yeah, it's exactly the same. What's up? What do you mean? It does. I'm dividing it over here.
Wait.
You want me to divide the whole thing by?
Yeah.
Sure. I mean, it's the same thing.
It's the same thing.
Yeah. Here.
Oh wait,
Nope.
no, it is. Yeah.
Put it. Where do you want to put
Sorry.
it? That's fine. Okay. Real quick, plugging in. You should end up when you plug in with 46.6. What I want you to do for tomorrow. Oops. What do I do? Is the second part of this. Okay. Take all those numbers and the K that we just got. Again, K should be 46.6. 46.6 newtons per meter. 46.6 newtons per meter. Okay. And I want you to calculate the velocity at 30 meters above the water. So she should be moving, sorry, speed, my apologies. The speed, 30 meters above the water. That's what I'm looking for first thing tomorrow. And don't forget, we do have a lab tomorrow, so please try to look at that lab ahead of time, just to get a general sense of what we're doing. Not a ton, but just a general idea of what we're doing. Bye-bye.